Thanks a lot. So today we are going to talk about deep learning using Apache MXNet on Amazon Web Services. But before I get started, I just want to get a quick poll to find out who here has an AWS account or who is familiar with Amazon Web Services. Great, great. This is pretty much a no-brainer nowadays, right? Almost everyone now has an AWS account. When I walk on the floor, I meet a lot of companies out there, and then I get to talk to them, and I'm like, hey, I work for AWS, and they go, yeah, I have an AWS account, which is great. So I am Mbanga. I've been with AWS for a few years, and I had different roles. I started as an ops manager and building the big data support team. And then I evolved as a technical account manager, working directly with customers and then helping them with their big data workloads mostly. My background is in physics, and up to recently, I started working as a business development manager for our AI strategy. And that's what we're going to get to talk about today, artificial intelligence on AWS. For a quick starter, you know, if there's something that you want to take away from this conversation or this talk, these workshops, we are going to cover a very quick summary of AI, what it is, so that we get on the same line. And after that, we will get into the actual agenda of the talk. So artificial intelligence is technically a way to structure or interconnect the world, the physical world, with learning or model training and things like that, right? So there's this conflated vision or view of machine learning, artificial intelligence, and then deep learning. And then this slide is basically a way to clarify that, what is into what. So in artificial intelligence, you want to extend the intelligent aspect of, you know, computers out to the real world. So you use machine learning to do that. So the machine learning part of the whole AI spectrum is to fit models or statistical models on data, right? And then when you get deeper into fitting models on data, one of the ways that you can do that is by using neural networks. And neural networks, deep learning extends the concept of neural networks by fitting a structure to data. So something interesting happened, you know, over time, and we're going to get to talk about it. But the Moore's law basically says that, you know, the compute capability doubles every year, and now we're at the point where we managed to get incredible compute capability using GPU. And the extreme parallelism aspect of GPU, we're going to get into the details about that, really enables the concept of deep learning. Right, so deep learning is an extension of machine learning, and then with the GPU capability, you are able to do a lot more. And we have a couple of examples to talk about that. The first one is image captioning, right, where it's possible for, nowadays it's possible for an AI intelligent system to basically receive an image as an input and generate a description of the image as an output. Essentially, you could take a picture of this room right now, and the model would be able to tell you a number of people are sitting in a room listening to someone speaking or whatever. Another application is into speech recognition, where you can pass, you know, the Alexa of the world, where you can pass speech to a deep learning model, and it would be able to do what we call automated speech recognition, and essentially understand whatever someone said. The third example is natural language processing, and it goes on and on. Automated systems in self-driving cars or medical image analysis. A cool example that we get to talk about often is the neural art, where you can essentially teach a deep neural network or a deep learning model how to draw, and or how to emulate or simulate the style of a certain artist. And which is the case here. So this model was trained on GPU, and essentially it was capable of replicating the artistic style of Vanguard, I hope I say that right, and then essentially come up with that image. So the concept of AI started quite a while ago, like in the early 30s or 50s, and then the first generation of human-computer interactions was in machine-oriented, when back in the 50s, you had to come with the instruction, you had to come with the data and the operations, 1 and 1 plus, I want you to do this for me. The second generation was in control-oriented and translated human-computer interactions, and that's what we are used to nowadays, where you go to a website and you have a set of instructions. You browse a menu, and then you click on, you're almost controlling a system. And then back under the hood, these control operations are translated and passed on to the machine as actual language that the machine can understand. The third model, and the model that is becoming prominent nowadays, is the intent-oriented model, where you speak to the machine, and the machine should be able to understand what you say, and it should be able to carry on certain actions based on what you said. And that's what you're seeing now with a lot of chatbots, with Alexa, and a bunch of other models that are essentially based on understanding what you are saying in natural language. So with that description of machine learning and then sort of understanding where, artificial intelligence and then agreeing on where we stand, here's what we're going to cover today. We are going to cover a little bit of historical aspect of deep learning. We are going to cover the potential of deep learning as of now, the impact of speed and big data on deep learning, and then we're going to get hands-on on Apache MXNet, just so I get to demonstrate a tool. I'm also going to get to talk about the AI strategy at Amazon Web Services. So quick poll, who here is familiar with Apache MXNet? Seriously? You have never heard of Apache MXNet? You have? You have heard of it? I have a lot of work to do. So I have about 500 business cards. They are available here. You will be, grab that. We have a lot to talk about. Great. So we have a lot to cover, so let's get started. Typically, these are just color coding. You will understand why I have that on a little later. So going back in the days, I wanted to put a sort of timeline together just for us to know where we come from and where we stand and then where this whole concept is coming from, right? And it's interesting that for many people that get to talk about deep learning or neural network, the first example is always the perceptron network. And I wanted to put this on to show that perceptron is actually later in the game. Like earlier on, like back in the Turing test, where Alan Turing wanted to find out if a human could speak to a machine, and then the machine would be able to respond, but a human wouldn't be able to tell who is behind the machine, essentially, right? So the concept of connectionism or connecting people or networks and stuff like that started in the early 30s. And so there were multiple attempts to deep learning or artificial intelligence essentially back then. And all of them basically failed because of a few issues that they had. One of them was the compute capability. The mobile phone that you have nowadays is more powerful than the most powerful computer in 1940 or 1950s. So they had that limitation, right? And the other limitation was the availability of data. In the 80s, they tried to create what we call the knowledge representations of the world, but they just didn't have the data model of the world and the ability to represent what humans are actually doing in the world. But nowadays, using a Fitbit, using different lots of other devices, we are basically generating a mountain of data every second, right? So the availability of data was a challenge. The compute capability was a challenge. But the idea of deep learning or the idea of artificial intelligence and the early networks or neural networks were already there. So the first half of this timeline is the traditional model, and the bottom half of this timeline is the deep neural model. So with a bit of color coding, let's observe what happened over time. So after the early attempts in the 30s and whatnot, you can see that this slide shows basically that there was a lot of development in machine learning, in traditional models. Some neural networks were still like algorithms or concepts or ideas were still written down, but they had the challenge of again, compute and availability of data. But I like this slide because it shows that around the end or the beginning of the 90s, people were already sick of supervised learning. they were already out of it, right? They had been doing that, but it's incredible to see that back in the 90s, people were already started going to unsupervised learning. And I don't know if I don't know who here is familiar with supervised and unsupervised learning. I just want to make sure that we have a correct definition. Okay, that one is great. So supervised learning, you tell the learning algorithm what you're looking for, and it can correct itself based on that. And unsupervised learning, you let it figure it out. But so in the 90s, people already started going towards the unsupervised learning aspect of things. And towards the end of the 90s and then mid-2000s, that's where the concept of deep neural network or different neural networks started becoming, more and more prominent, right? And then it goes more and more. So I'm a little biased here because I'm talking about deep learning. I'm pretty sure there are other, traditional methods that are coming out, that have been coming out lately. But it's just interesting to see that over time, deep learning has been taking over in terms of academic research or papers or different type of networks and methods that are created. And just to close the loop on the whole concept of artificial intelligence, it's assumed that by 2027, machines and computers would have this, sort of integration where you wouldn't know who is who, right? And actually, some people take that to the extreme, right? They actually, give you the impression that the machine would actually look like a human, and there's this bit of a fear around what does that mean. I have my ideas about that, and if you want to talk about it, we can meet offline. So what do you need in order to achieve that much, the concept of machine and then human integration, or the concept of artificial intelligence? You need fast compute, you need ubiquitous data, and you need strong learning algorithms or learning platforms. Let's start with compute. This is basically the architecture of a CPU and the GPU. Digging into the CPU, for one core, it has a RAM like normal computer architectures, but it has a shared cache. And this is important in terms of difference between CPU and GPU. And it has a control unit that passes information to arithmetical and logical operations. But the point I want to highlight here is that for all these values, the CPU has a shared cache. But the GPU explodes the concept of control unit, RAM, and arithmetical and logical operations. I don't know if you can see that. OK, this is great. Where essentially you have distributed cache per arrays of cores, and it's possible for you then to do, I'll get into that. So this is a structure of a program. Typically, when you have a program in data science, that's what it looks like. So you would start by importing libraries, declaring variables, and doing a certain number of things. But over time, if you're doing deep neural networks, for example, you have a structure. You construct what we call a computational graph, and that's a structure. And on that computational graph, you have multiple passes of the same data set, right, in iterations. So GPUs are great for that. GPUs are great for what we call single instruction multiple data, because you have the same network structure through which you pass multiple passes of the data, and then you use intelligent optimizers or optimization method to do backpropagation and all that. That's the power of the GPU. You can split the network structure and share that across multiple multiple cores. And for the rest of the code, like declaring variables and doing other things, the CPU handles that. We're going to get into how MXNet does that natively, but it's a hard problem to solve, working with GPU programming. Back in the days, people had to do that manually, but nowadays with NVIDIA CUDA and some intelligent libraries, it's possible to do that natively. So at Amazon, we have, at AWS, we provide, at a high level, we provide, cloud services, virtual machines, and a certain number of things. And in 2013, we released what we call the G2, general purpose GPU instances. And I was excited about that. Like, I was completely excited because it had about 1,635 cores. I spoke about that to everyone, my friends and family. My brother is actually here. He's a data scientist. He's a real data scientist, not a keynote data scientist like me. But and so if you want to get to talk about the philosophy or the etymology of data science and physics, talk to him afterwards. But anyway, so I was excited about that, right, in 2013. But now, last year, we did release the P2 instance that has about 2,880 cores for the lowest version of it. The big ones have about 16,000 something cores. It's crazy, right? And it really opens the potential to do parallel type of compute that requires vectorized data set like matrices and tensors and images and voice. And we'll talk about that in details. So this is the first part of the demo where I show you how to launch a P2 instance on Amazon Web Services. And praying to the gods of the demo that everything goes well. Now I need to mirror. Just give me 1 second. You're not seeing anything. Okay, sorry about that. Can you see everything all right? So when I started in 2012, 2013, there was it was possible to go on the AWS console and just know everything that's going on there. There were just a few services and a few products, but nowadays you have to search for it because we basically release, for a developer, we have 3 releases a day on an average. So even for us internally, it's very tough to keep track. But we have a lot of training programs. We have a lot of training mechanism to make sure that people are up to speed with what we release. So this is Amazon EC2. That's basically where we get started with launching machines. And it's really easy to launch a P2 instance on Amazon EC2. That's a process that you use to launch a machine. And we do have what we call the Deep Learning AMI by AWS. And the Deep Learning AMI stands for Amazon Machine Image. It's essentially us taking on the responsibility of installing all the necessary libraries that you need to run a successful deep learning workload at scale on the cloud, right? So I'll get to dig into what the deep learning AMI has, but if you go on the marketplace is that environment where different users and system integrators and technology vendors can share a copy of an image of a machine that they have built and potentially apply a licensing model on top of it. So this is a deep learning AMI, right? So we have pre-baked this machine for pretty much everything you need to run deep learning at scale. So you go through the process, and if you look up GPU compute, you find the different version of P2 instances that we have here. I think I was looking up the 16 exahash P2 machine, and that's the one I said has about 16,000 cores. So it's incredible what you can do with it. And the whole concept of a cloud, the agility, and then the elasticity means basically that for testing purposes, you can launch this machine, get it to run for a while, test whatever you need to test, or run the workload you need to run on it, and then turn it down and pay for what you need.
You have to pay for 3 times more?
No. Yeah, it's just for...
16,000.
Right. Yeah, so 16,000 cores, that's all I need. So the machine has a pricing model. I don't like keeping track with the pricing because we reduce prices fairly all the time. And actually, yesterday, we did reduce the price on one of the instance families of EC2, the M4. So the best way to know how much it is to just look up the price, before you launch an instance. But it's relatively cheap. And we have a lot of pricing models where you can, pre-order and get a discount and stuff. So, and it's pretty much it. After you select the instance type, you go to add some parameters. Like I have a cloud VPC. A VPC is a virtual private cloud. It's basically a virtual data center that you have in the cloud. And then I give it the role. A role is basically the access control capabilities or the power that you want to give to that machine in your cloud environment. And you give it a public IP if you want. If you don't want to, if it is connected or you want to access it via VPN, you don't give it the public IP. You add storage to it. You add a tag to it. A good practice using tags is for having the data science department tagging their machines with data science, and then the research department and sales or whatnot. And then you can generate reports based on tags, and we've seen enterprise companies using the tags actually for chargeback within the company, right? And then you can review that in launch, and then you click launch. And you have a security key to access your environment, and then you hit it. That's pretty much it. About 5 minutes later, you have a deep learning environment running on the cloud. So that's it. So I'll get to show you what it looks like in a second. Sorry, I will be doing this back and forth. Okay. So let's talk for a minute about our strategy around AI at Amazon. At AWS, we have a number of services that revolve around artificial intelligence, and we put them in different classes. The top class there, where you see AI services, that's basically us taking up the responsibility of training and preparing deep learning models in the backend and exposing them via an API for users or customers to use. Now, the idea here is that some people don't want to train models, right? Some people don't want to go through the pain of training models. It's a hard problem to solve. At Amazon, we've been doing that for a while. We don't talk about it often, but we have been doing that for a while. Collaborative filtering is happening on the Amazon.com page, where people who bought this look like people who bought that, so they might want to buy this, things like that, right? And so we have a lot of experience internally doing machine learning and deep learning at a very, very massive scale on a very, very large amount of data. That's why we've released a few services that enable people to use the capability of deep learning or machine learning without training models themselves. Amazon Recognition is one of them that basically allows you to do a few things like object recognition within a scene, face matching comparisons, or just feature labeling on an image, where you can pass an image through a recognition system. You don't need to know what's happening in the back end, and it returns a list of labels, like this person, this face, this is a face, the face looks happy. I think it used to or didn't used to, I can't confirm or deny, but maybe it had a beauty score at a point, and then we didn't want to take it out. Anyway, but now it can compare, it can give you an age range as well, and we keep improving that with the data that we get. Amazon Polly is our text-to-speech solution that enables people to pass on a piece of text, and it would respond to you with a speech, and that's actually what is behind Alexa. That's what Alexa uses to speak to people. Amazon Lex is the engine inside of Alexa. It does automatic speech recognition and then natural language understanding. Again, if you want to solve the problem of getting a voice input, removing the noise around that, flattening that down, and understanding the intent within that voice input, Amazon Lex does that for you as a service. So you can leverage Amazon Lex to build a chatbot that, without having to worry about, solving the problem of inputting the voices and understanding what the user is saying. Now, after that layer, for the people that actually want to do some extra machine learning stuff like training a model, we have what we call, the AI platforms. Amazon Machine Learning was our first machine learning product that we released. It basically has 3 services: linear regression, logistic regression, and multi-class classification. So it doesn't have the full extent of the capability of machine learning or deep learning, but again, it was useful for the people that had these simple problems and wanted to solve that. And it's also a service. What you do with Amazon Machine Learning is that you hand over your data, we take it, we train it, and then we put an API on top of it for you to consume it. For people that wanted to train data themselves at scale, we have Amazon Elastic MapReduce that basically enable people to launch a Hadoop cluster and use Spark ML and stuff like that to train models. And Spark ML is there. So going deeper into the stack, we have what we call the AI engine, so the deep learning engines. That's for the hardcore data scientists that actually want to use the state-of-the-art, latest ways to build and train your network in order to get their work done. So, and that's what is in the deep learning AMI or machine image that we just launched. So we have prepared a machine that has TensorFlow in it. It has Caffe, it has Torch, Theano, CNTK. If you're familiar with deep learning, you know what this means. And Apache MXNet is one of them. Right, MXNet is, and that's when I get to talk about it, but MXNet is a deep learning library. It's a project that started at CMU and University of Washington, a few folks in academia. And essentially, it tries to solve the problem of deep learning at scale. Right, we're going to get to talk more about that, but it's a project that is backed by AWS, and actually a good number of the contributors or the folks that started MXNet work for us now. And we are making it the core, the core of our deep learning strategy, right? So we do have a lot of services and products, and we do inject, learning capability in these services. And you will see over time more and more that our future releases of products like EMR or ECS or other services have the deep learning capability, embedded or injected into it, and then that will come from Apache MXNet. So we're pretty much excited about that. And at the hardware level, we do have the P2 instance type that is GPU capable that I just spoke about. And then we also have EMR with Spark. Our ECS solution is basically Docker at scale on the cloud. Enables you to launch a fleet of machines that have the Docker capability. And Lambda is a serverless compute. Who here is familiar with Lambda? Good, 50%. So Lambda brings computing up to the stack where it's event-based computing. If you have a piece of code or an operation or a logical operation that doesn't really require you to run a machine, we would run the machine for you, and you just drop your code on Lambda with a listener, and then anytime the listener is invoked with an input data set, it would generate an output, and you don't need to worry about managing that extra compute capability. And you pay us per request. So that's pretty much our approach to artificial intelligence. We go full stack from hardware to services, but we're going to focus on the AI engine part of it. So Apache MXNet. Like I said, MXNet is the product that we do backup. Our CTO wrote the full blog post about the reasons why we decided to choose MXNet as a deep learning library. And if you want to get a bit philosophical about that, there are a lot of libraries nowadays, and there's a lot of them that do multiple things. And people sometimes have the idea of using all of them together, but really, you need to choose one, right? And as a provider, at AWS, we also had to choose one that we thought had some capabilities that we thought were valuable for the pool or the array of users or customers that we have, which is nicely all of you, right? So the reasons that we chose MXNet are basically the flexibility, the portability, and high performance. We're going to talk a little more about that. From a flexible standpoint, I think MXNet is one of the only libraries that supports, if not the only library that supports all of these languages, right? So it has the same underlying core engine, which is extremely fast. It was built in C++, but it has binding languages. It uses binding languages in C++, Python, Scala, R, Julia, JavaScript, MATLAB, and Go. Right, and more. Right, so MXNet really has that capability, that way to put developers with whatever language they're familiar with at ease without compromising the speed or the capability, because the backend is the same, it's in C++. It's also portable. right? When you build model with MXNet, you can essentially deploy that anywhere. And we'll talk more about that, but this is a value add. I spoke to a lot of customers, and they had a challenge building models with certain languages, and then writing requirements and specifications for the actual developers that had to put the models in production. The customer told us that they write 30 pages of requirements after they are done figuring out the logic, and they hand that over to the developers, and it takes 3 to 6 months for the developers to write, the code to put the machine learning model into production. So it helps that you build your model in the language that you would use to deploy that. And it also helps that the library that you use is lightweight enough to operate at the massive scale or at a small scale like a computer or an iPhone or drone or something like that. MXNet is also high performance. So we talked about it being flexible and lightweight, but it's also high performance. Oh, Siri is responding to me now. I'm sorry, Siri, I'm not talking to you. Sorry, guys.
Good evening, ladies.
Uh-oh.
Shall we start with O'Donnell's?
No, don't start it.
I can tell your body's been lacking the pleasure of satisfaction your body deserves.
That's R. Kelly. Sorry, guys. So Siri just started playing my music, and then that's how I'm on the news now. So MXNet is also high performant, right? In the sense that it can operate on a GPU at scale and within the same machine, but it can also operate on multiple GPU in multiple machines at scale without the need for a developer or user to change their code. And if you want to solve that problem again, the problem of putting multiple machines together, it's a massive challenge, like message passing between the machines in a cluster, state synchronization, and then data synchronization is a hard problem to solve. So you need a library in the back end that does all of that for you without you worrying about it. We actually ran some benchmarks, and in terms of scalability, these are some state-of-the-art networks in the deep learning ecosystem, right? You guys are probably familiar with Inception, AlexNet, ResNet, and all that. So the x-axis is the number of GPUs that we use to scale, the learning on the network, and the y-axis is the scaling factor. So the ideal case would be if you had a model that you would train in 2 hours, and then you double the number of GPUs that you use, then you should be able to train that in 1 hour. But cluster management and message passing and data management across the network is a challenge that makes it impossible for any library to attain the ideal use case. And we have trained multiple models with MXNet, and there's a benchmark that I'll share with you after, and it reaches 91% efficiency sublinearity, which makes it extremely efficient. Another concept around MXNet is what I call big, small, and fast, where you can train your models at scale on the cloud and test them or deploy them on devices at the edge. So I believe that you will be hearing more and more in the industry about this concept of, train in the cloud, deploy at the edge, where you want a deep learning model to be able to operate on a very, very small device, leveraging the training capability on the cloud. So what happens is that you would start by training a model, and then you would, after you're done training your model, you basically have an artifact in terms of the model in terms of a zip file or a JSON file, and then you store that on the cloud, maybe on ECS or Amazon S3. And it's possible for you to grab a copy of that model that is serialized well enough to run in a browser and push that to a JavaScript library or something like that running on any operating system on the field. It's also possible for you to have a smaller copy of that model that you push to a mobile device, same model, right? You push to a mobile device or a drone, and it runs in the field. So again, you want to be able to train models on the cloud and then deploy them at the edge. And then this is a practical example, right? Where someone, I don't know if you can hear, but oh, it's a bummer, you can't. That's another, so these are 2 examples. The first example is someone it says the name of the banana right there. You couldn't capture that, I'm sorry, but the sound is coming from my laptop. And the second example is a guy that wanted to follow his girlfriend around, so he built a model with a drone to do that. So both have, so the concept here is that the first one does image recognition, and then it's sad that you can't hear the sound, but what the model is saying there is banana, orange, espresso, and things like that. So there is a camera that just grabs the picture of an image in real time and then passes the frame to the model, and then the model analyzes what it's supposed to do or to be, and then it's not connected to the cloud, not connected to the internet, and then it responds to the user with voice. So it's called Blind Tool. It was an experiment. It was a Kickstarter project. And like I said, the second model does image recognition using drones. So let's move into demos now. And to prepare the demos, I wanted to go around, do a full go around, the different concepts around deep learning or big data. Or I wanted us to follow what you need to do typically, and us to follow the MXNet API that would sort of help you to do that. So a quick time check here. OK, I have enough time. So the first concept in deep learning, like when you want to start training models and when you want to start working on models essentially, is that you need to vectorize your data. You start with your data, and then you need a data format that your learning models will understand. So most of them work with what we call tensors. And tensors essentially are ways to represent data. The one-dimensional tensor is a vector or an array. Two-dimensional tensor is a matrix, and then the more you augment the dimensions, the more depth you get, and you can have the 4D dimension, the 5D dimension, and the 6D dimension. And as you can see there, the structure of a tensor makes it extremely parallelizable. It looks like a GPU just by looking at the picture there. So if you have a 6-dimensional tensor, for example, it's possible for you to pass that onto a GPU the way we saw the GPU looks like in parallel, because you're only passing multiple cubes or batches of the same data set over and over again. So tensors have a structure that works extremely well with GPUs. That's why it's used. And let's go back to tensors for a second. Oh, this is not doing what I wanted to do. OK. So the second concept is the neural net. Right? You need a neural network, and then the API in MXNet that is used to build a neural network is MXNet.symbol. I used this slide, and I didn't make it. It's the author is there. It's a good. I encourage you to look that up. It's a good catalog of many of the different types of neural networks that exist nowadays, right? Where you have from the perceptron to the feed-forward. The feed-forward neural networks are essentially fully connected neural networks that you can attach, a predictive output layer to. And then it goes deeper into convolutional neural networks or LSTM or get recurrent units neural networks. And then all of them essentially extend one concept after the other, and they add certain capability or certain types of neurons or certain types of gates. And it goes deeper into other encoders that are basically used for feature engineering and understanding. So let's talk about convolutional neural networks for a second. What you do with CNNs or convolutional neural networks in the concept with the example of image analysis is that you take an original image like that one and you break it down into a certain tensor of different, of a dimensional size that is usually the height multiplied by the width and then the depth of an image, depending on whether the image is red, green, blue, or red, green, or just black and white. So you decompose the image into a tensor, and then you pass that tensor through multiple layers of the network, right? And then as you pass the image through multiple layers of a network, what essentially the network is doing is that at each layer, it's learning certain features. So it has filters attached to different neurons in different layers of a network that learn edges, learn the initial shape of a face, and the output would actually be a certain face. So that's the concept of a convolutional neural network. And the API endpoint in MXNet that helps you to do that is a symbol. And then the third concept is the training. You want to train a model. And for training a model, there are multiple libraries out there. And again, so this, I put that down there for it to be scary enough, but it's actually not. So this is the loss function, like the log loss function. It looks like an entropy function if you're familiar with it, right? So where essentially you do some predictions, and after you do the predictions, you have this error function that tells you how far you are from reality. And then that error function is parameterized. Now, the art or the benefit of a deep learning library is in the capability to minimize this error function. That means deriving that, doing gradient descent, and all the nice stuff that you guys are used to, and getting to the best possible, so the lowest possible error by updating and changing these parameters. Now, there are two ways you can do that. One is that you can serialize that, with a CPU and whatnot, or the library can just serialize that, because as you do what we call backpropagation, you need to maintain the state of the gradients. You need to maintain the gradients and then the weight and all these things. And it needs to work in conjunction because you're deriving the whole function over the whole weight of the network. So intelligent deep learning libraries are those that can do that within the GPU so that they can do that at a massive scale. And instead of being serialized like the case down there, it would actually be parallelized where multiple machines with multiple GPUs across the network are working simultaneously, but they have a way to update the same weight at the same time, right? So state management, and there are some heuristics that happen in there, and that's one of the benefits that MXNet module, which is the tool that you use in MXNet for you to do that. So it does automatic gradient computation and then update of the weights. So the other thing I want to talk about in terms of optimizing network is how you it's the initializer and the optimizer and the learning rate scheduler. Who here is familiar with the vanishing gradient problem? Okay, a few people. So the vanishing gradient is essentially the fact that as you compute gradients over a massive network, originally neural networks were very shallow, so that it wasn't a problem. You could derive with respect to the weights within the network and then come back to a very good derivative. But as your network grows, you have more and more issues with your gradient just vanishing. And these are two examples with the recurrent neural network and the long short-term memory network, where the RNN has the gradient vanishing rapidly because the network is so large that as you start deriving from the output layer back to the input layer, the gradient is very, very, very infinitesimally small, right? So there's not much change happening anymore. That's why the long short-term memory came on as sort of an improvement on a recurrent neural network, where it has memory, so to say, it maintains states, and it allows you it allows your gradient to vanish with a little less time. The other one is the optimizers, where we have multiple methods of optimization nowadays. People are familiar with the gradient descent or stochastic gradient descent, but if you see there are many other ways to optimize your neural network. The gradient descent basically computes the gradient or the derivative on each input data set, right? It's slow, and it doesn't get to the accuracy on time. What you do in deep learning is that you pass data multiple times through the network. We call that epochs. An epoch is the passage of the entire data set once. So sometimes you have to pass the same data set multiple times through the network. And you realize there that with a gradient descent, stochastic gradient descent, you need to do that multiple times for you to reach the optimal accuracy. But there are other innovative optimization methods like the ADAGRAD that essentially gets you to the minimum of the loss function that we talked about earlier a lot faster, right? And the second part of the chart there is the area under the curve, where you can see that it actually gets to optimizing your network rapidly. And this is money, right? This costs you money. So the more time you spend training your network, in the AWS world, for example, we pay you per hour. You pay us per hour of usage of your machine. So if you optimize your environment with a library that is smart enough to get you to reach accuracy faster, or to get you to reach the minimum of your function faster, then it saves you time, it saves you multiple other things, right? And in MXNet, we support that automatically with the initializer method, and then the optimizer, and the learning rate scheduler. The learning rate scheduler essentially allows you to drop the learning rate over a certain period of time, depending on how long your network is supposed to run. Okay, so the other concept I want to talk about here is the concept of scale. I mentioned that when you train a model at scale, there are a few things you need to do. You start initially with a data set that is like that, right? It's broken down into batches, and multiple batches are in the same, what we call iterator. And the first thing that you do is that you read the data partitions in parallel. It's the same data set that you pass through multiple GPUs, right? Read that in parallel, and then you have an external key value store. That's by the architecture of MXNet. And the next thing you need to do is to pull the parameters of the loss function. You need to pull them down to the GPU from the external key value store. And then you compute the gradients. And after you compute the gradients, you push the parameter back to the external key value store. And after you push the parameters back to the external key value store, you need to update the weight, and then you go over and over and over again. So that's how multiple GPUs within the same machine work with an external KV store. And so the KV store its role is just to like serve the weights and serve the gradient, right? That's very easy. And the GPU does the actual processing of the data. And so if you want to move from a single machine to a cluster of separate machines, there's no change required on your code. Again, scalability is almost a no-brainer from a developer's perspective. So yeah, and the last concept that I'm going to demo is the concept of inputting or iterating through data. So now we're going to move into the demo, the part that I bet you are all waiting for. Just give me 1 second. Okay. So the first example I want to show is how to, so I mentioned earlier that MXNet runs with multiple machines and uses multiple languages. So the first example I wanted to show you, because I figured, this is a data science conference, I wanted to show how MXNet works with R, right? It's very native. You just launch the machine, and I've done that already. So this environment is connected to to another machine that I launched before, and I was testing that. And I'll walk you through the different APIs the way I mentioned them earlier. And yeah, so this example looks at, people think that deep learning is all about image analysis and all that, and it's actually not. Most of the deep learning libraries can do the other type of learning, like regressions and all that type of stuff. So this first example is about the credit default analysis in the banking environment using MXNet. Can you see everything clearly? I was testing before, so I'm going to remove the parameters. Just bear with me. So in this example, I load MXNet as a library, right? I just do require MXNet, and it does that. So after I load MXNet, vtreat is another library and that's why I like R, because vtreat is used to essentially do feature engineering, like centering the data, scaling the data, and a bunch of other things naturally for you. Ranger is a library that you can use for random forest very rapidly, right? So you can either do it yourself with a carrot package, or you can do it with Ranger automatically. So that's that. So the extensibility of MXNet allows you to be able to essentially create your own accuracy metrics, like this one, the log loss. So there isn't a multi-class log loss error function within MXNet, and it's as easy as this to essentially do it yourself, right? So I do that. So we're going to build the network and then sort of do that together, and I'll explain the code as we go. So after I add another metric for log loss, what I'm doing here is that I create an accuracy function, right, that I'm going to use afterwards. So nothing to do with MXNet here so far, except for loading it. Is it big enough for everyone? Okay, sorry about that. So, is it better? Okay. Okay, so the next thing that I do is that I read the data set, right? It's a CSV, and then let's just look at it together. Let's just look at that together. Oh, I'm building a function, so we're gonna look at it later. Okay, so after loading the data set, I do a couple of transformations, like converting categorical data set as factors, like sex, education, marriage, and stuff like that. So far, this is all R stuff. And after that, I'm just sort of preparing the data for passing that into the model for training. I set a seed, so I get a certain consistent set of random numbers. And this is the magic of so here I'm building the training and testing data, where I get the training data to be 20% of my data, and then the testing data to be 80%. Sorry, the reverse. And I set the target, and then the variable names and all that. And then this is where the treatment starts, where you can basically say, design treatment for my training data set, and what it's going to do is that it's going to automatically do all these things for you, right? It's going to check the columns without variance, and then remove that. It's going to check outliers, and then treat that, and a bunch of other things. So it's a good library for testing if you don't want to do all of that yourself, or for demos. Now I start building the network with MXNet, and building the network is, so we spoke about the symbol API that essentially allows you to build a computational graph. And here it's important to talk about the concept of declarative and imperative programming. In symbolic programming or declarative programming, are you guys familiar with Chef, Puppet, or configuration management utilities? Usually in those utilities, you just go around and say, hey, I want a web server, and you don't need to know how the backend system gives you a web server. That's a declarative language. It's good for graph computations because you can build a graph ahead of time, a directed acyclic graph, and then on the graph you can do some optimization before you actually compute it. SQL is a declarative language, for example. So MXNet, and actually the name of MXNet is mixed network in the sense that it supports both imperative and declarative languages. You can build computational graph while you still have the imperative declaring variable and then running a logic the way you would have in Python aspect to it. So here I'm using the symbolic declarative language aspect to initiate a variable. And then after I get a variable, that's the placeholder for my data. I add a dropout layer, right? I want to drop 10% of everything that comes in, and dropout is a way to prevent overfitting in deep learning. After that, I create the fully connected layer. Fully connected is basically a linear transformation. And on top of the fully connected layer, I do a batch normalization, right? Which means that for every batch of data, I want to apply normalization. And there's, again, an inbuilt function to do that. And on top of the fully connected layer, I add an activation function. And the activation type in this case is ReLU, it's rectifier linear units. Now, the thing I want to call out here is every input of the first layer, every variable of the first layer is the input of the second layer. So we're passing the data here. We have that. And then on the second layer, we're passing, this second input. And on the third layer, we're passing the fully connected layer to the batch normalization and so on. So we are building this chain of operations, or this graph of operations over time as we go through it. And this viewer on the other side actually graphically shows you what you're doing. So in this, we still defining the structure of our network. And then we start building a second fully connected layer, right? Where we do element-wise addition here between two layers, another batch normalization, an activation, and then we add another dropout layer. And again, I was just doing this for demo purpose. And the third thing is that we do another fully connected layer, and this is interesting. This is a linear regression output. So you also have a symbolic item for a linear regression. So essentially what we're doing here is that we are doing logistic regression with MXNet, with neural networks. And in typical logistic regression, you have the inputs, and then you build a linear combination, and then you apply the logistic function on it. So it's like one pass of the data. But here, we're using neural networks to have multiple layers in the neural network before we do the logistic regression. So we get the opportunity to learn features and features and features of the data and use backpropagation to sort of treat the data over the network before we do logistic regression. So the assumption is that it's deeper than the traditional logistic regression. And after creating the logistic regression layer, I start working on the model now. So there's this function called model feed forward create that essentially creates a feed forward is a pass through the network. So at this point, I'm binding the networking structure that I created to the actual data that I was working on before with V3. So I bind the data to the training data and test data. I add an initializer. We talked about an initializer to the environment. And I give, okay, done that. It's okay. So I give it the type of optimizer that I want to use from it. And this context part is interesting. So in this case, I'm using the CPU to run the computation. And it's as easy as changing this context from MX CPU to MX GPU. And I have another example with GPUs for you to run your computation on your GPU. So as I do that, and then I pass the symbol to that feed forward command, and the number of times I want, oh, I've been getting errors so far.
You need to rerun line 70.
Line 70, the initializer. Expected comma. This is the part where you swear that the demo was working before. Okay, so 66. Okay. Perfect, thank you. And I pass the context. Okay, so what I was doing is that I was binding the data to the network structure that I created. And as I finish binding that, it starts training the network. And as it trains the network, it basically reports, the accuracy or the error over time, right? So I ran this before, but I'm going to run it again. This function GraphViz essentially plots the structure of the network in this viewer. Where are you? Come on, come on, come on. Yeah, here we go. So, no. How do I pop this out? Like this. Is it clear? So the graph visualization function shows you the structure of your network, right? It shows you the computational graph overall, and then you can play around with it. I made it simple for the demo, but you can add the weights to it, and then there are ways that you can actually have interactive ways to see the graph over time. So it shows you what we've done essentially so far. We've had the dropout, and then we had a fully connected layer batch normalization, first activation. We did an element-wise addition, and then we added batch normalization again. So you can, this is a fairly complex logistic regression, but it's for demo purposes, right? So to show the art of the possible. So moving on, I start, predicting on the test data, right? So I'm building the prediction, and I'm passing the log clause there, and I'm going to, that's a prediction, and the reason why I'm not showing that now is because I want to compare that to random forest. So I use Ranger to do random forest pretty much automatically. You could check the documentation for Ranger. It's a lazy way to do random forest, and that's done. So at this point, I'm comparing, the accuracy of, with MXNet, and the accuracy of my second type of model, and compared to the accuracy with the random forest, right? So the cool thing here is that the error went down by just 0.42 compared to 0.43. So the random forest is still very, very good for logistic regression, but the deep learning network did a little better, right? That's the point here. And that's that about this example. The second thing I want to show is, so in MXNet, we have a lot of notebooks, a bunch of examples. They're available on GitHub, and I'm going to show you the link to go get that. And just browsing through the notebooks that are available here, and there's a lot of information on how to essentially, launch that. And browsing through all the notebooks, I don't know if you can see, well, you have this original outline. I actually have it here. So this is actually running on my machine on the cloud. So you have this original outline that has a lot of examples that you can run with MXNet, right? It's a bunch of, and then so it's an open source thing. The community is working on it, so you can do your example and add that on there. But it's a bunch of them. A lot of people that work in deep learning know about the MNIST, example, and a bunch of people know about, image recognition, LSTM. So we are constantly working on multiple examples and populating that on that, populating these notebooks, and it's free to use. You can just go grab it. One thing I want to mention, though, is that you don't need to use it on the cloud. You can just run it on your machine, because MXNet can also run on your CPU. So the first example that I'm going to run here is the traditional MNIST example for image recognition, to recognize handwritten digits. So we're going to do the same type of things that we've done earlier. This part of the code is just to load the data. Here, I'm just grabbing the MNIST data set. And in this part of the code, I'm visualizing the MNIST data set. So the handwritten image recognition exercise is basically about using, training a deep learning model or training a learning model of any sort for it to be able to recognize whether a digit that was written with a hand is a 0 or 1 or 2 or 3 or 0 to 9. So it has 10 outputs from 0 to 9, and the input is the image, and the output is supposed to be the character or the digit that was typed in. And this is available, so you can read the text later. But here, essentially, what we're doing is that we're building iterators, right? Because we have a lot of images that we pass through the network for training, and we pass them in batches. So we sort of need a structure that iterates through these images and passes that over to the network. That's what we've done here. So we're building the tensor, essentially, and then we're using the reshape and the n-dimensional array iterator capability of MXNet IO to do that, to run through the data. And then, so we're going to use a multi-layer perceptron, which is basically linear combination after linear combination after linear combination and activation to tackle that problem initially. So to do that, we do the same thing we did before. We create a variable initially, and then with the variable, we flatten that, right? So here, the structure of this network, I'll explain that before we continue. We grab the image, we create the tensor off of the image, so we flatten the tensor, and then we build a tensor of these tensors of each images, and then we create batches over them, and then we pass that through the multi-layer perceptron. So we flatten the data, and then we create fully connected layers, which are, again, linear combinations. We activate that with ReLU, and then we create another fully connection and activation, fully connected, and finally we create a softmax output. So the softmax output layer in neural network is one that allows you to predict one of many classes, essentially. It's a multi-class classification output layer, so to say. It does more, but that's the easiest way to explain that. And after that, I use this plot network function to essentially visualize the network. So if I run this, what just happened? Oh, I created this machine. Okay, let's troubleshoot this together. So this is live troubleshooting session 1. I created the machine without installing the GraphVS library, so right now I'm connected in the P2 machine that with the deep learning AMI that I launched, on the cloud. So let's do this again. See, yay, worked. So this function, this plot network function essentially shows you the graph that I mentioned. And see, this is a little different from what we saw in R, where it actually, shows you the structure, like the weight and the structure of the network, what are the inputs and stuff like that. So an input image is 27 by 28, I think, 27 by 27, and so you pass that, 28 by 28. So for each image that has 28 pixel by 28 pixel, and because these are black and white images, it only has one channel. So that's the initial structure of the data when it's flattened down into an array. And then the fully connected layer essentially explodes that initial input space, right? Creates 720 something. Outputs, 128 outputs out of it. And then you can just go on and on and on and on until you start reducing the space, the input space that you're creating. And that's actually how the network learns, by creating multiple combinations of the same thing and doing linear combinations around that. And then you inject the softmax label, the actual real labels of the images. Like you pass the image to the left, and then you pass, because this is supervised learning, you pass the label to the right, and then as softmax happens, the network realizes, wow, okay, I trained this and I thought it was a 7, but it's actually, I don't know, a 9, I made a mistake, and it propagates the error back through the network using back propagation that we talked about. So high level, that's how it works, and you can visualize that on this Python notebook. Now the next thing that we're going to do, so we have created the network structure. We didn't bind that to the data, and we haven't started training the model yet. Now we just enable logging, and then we use a feed-forward method to essentially bind the symbol again to the data. And as we do that, the training starts on the CPU. I have another example of training on GPU. So there are other speed and then metrics around this concept, the library that essentially would report on the number of samples that were trained and then the accuracy over time and then the custom time. And it resets the iterator. Like I said, the way this learns is that after a full pass of the entire data set, you reset your iterator, and you do another full pass of the entire data set over and over again. So a full pass is called an epoch, and then you train over multiple epochs in order to have the accurate data set. So after that, I'm actually doing a sample test here where I grab, so where I show a sample right there. So I pass one of the images that is supposed to be a 7, which is here. We can't see it, but and then I get the model to predict that. So it predicts it with a sample probability of 0. So it's fairly sure that this image is a 7, was classified as a 7. And it's also giving you a validation score. So the notebook is available. You can follow that later on. But the cool thing with Jupyter Notebook is that you can actually inject some HTML in it. And with a little bit of HTML, we can do some fancier stuff. So let's do a little exercise. So we've trained our model, and now let's test it. We're going to create an image of, my drawing skills are terrible. So what's your guess? What do you think the model is going to predict here? So you got that right? So you classified it as a 3. Now let's do this. Who knows this kind of 7? Oh, you do? Okay, my people. Oh, you do? Fine. So the MNIST data set though wasn't trained on this kind of 7. So what do you think is going to happen? Was classified as a 6, right? So you see, the data matters, right? Whatever you submit to your data matters to the end result. So let's do another one. If we do this.
What happens if you write a German 1? It's not just a,
Look at this one.
yeah.
It looks like a German 1, right? Not really, but let's do that one. But it got this 7 wrong. If we do this,
Yeah, that's a German 1.
it's also the French one.
Oh, yeah.
So why do you think it is so? I'll give you an AWS agenda and pen if you get that right. What? Sorry, I can't hear you. Right, that's true. I could have given it inputs that looks like this. But okay, let's do another one that illustrates the concept I want to. So why do you think it's seeing this as a 4?
Because it's measuring edges. Right.
Yeah, edges. So you're both getting agendas and pens. So we flattened the input data set, right? We've taken the data and then we have flattened it down in an array, and then we pass that to the network for training. So what we've not done here is taken into consideration the spatial relationship of our image, right? We're not going, the network is not learning like this, like, okay, this part is here or whatnot. It's just taking a flat array, so you lose the spatial relationship. So that's sort of, it's a segue into the next sort of concept of going through image analysis, right? We were analyzing images with linear combinations before, and we've made, we created a model that works somehow, but it's not perfect, and that's the case there. So the second concept is the concept of convolutional neural network. That kind of solves the spatial relationship within an image, right? Where you're not only looking at an image as a flattened array, but you look at an image with the regional relationship, right? You would take pixels that are adjacent in a way that is different from taking pixels that are separated. So not digging into the details of CNNs here, but they are very good for image analysis, high level, right? So they're the ones that would learn the spatial relationship between features, and it uses this concept of of filters, right? Where it does a convolution in math is basically applying a function to another in order to see whether it has a certain characteristics. So it creates a number of filters that it applies to the image at different locations, and based on this location, it can tell whether there is an edge there or whether that looks like a nose because it saw a nose before, and all these things. So it's a lot more advanced in terms of image analysis than the flattened arrays. And there's this concept of pooling that basically helps you to play with your input space back and forth in order to not explode the network. So let's do that. Let's create a convolutional neural network with MXNet. So you go through the same process, and we're pretty familiar with this already. So you have a symbol, start with a variable that's a representation of your data. It's not the data. And you create the first convolution layer with the kernel. The kernel is the actual filter that we talked about, and with 20 filters. So you want to, on the first layer, apply 20 different sort of characteristics recognizers, if I can find, for lack of a better word, in order for you to, at the first layer, learn some features. And then you activate that with hyperbolic tangent. And there are a few activation functions. You can get philosophical about which one is better. People have their thoughts about that. But ReLU is the one that has a lot more traction, had a lot more traction lately. And for one, one of the benefits about ReLU is that it's very easy to differentiate, right? It's equal to 0 if your input is less than 0, or equal f of x is equal to x if the input is greater than 0. And the derivative of f of x is 1, and the derivative of everything else is 0. So computing the differential of, or the gradient of ReLU is extremely easy. And the hyperbolic tangent function to differentiate that, you need to do some exercise. So, and then you do pooling, which, like I said, reduces your input space. So you could start with the number of filters that are like that, 1, 2, 3, 4 by 4. If you do a 2 by 2 max pooling, you're going to end up with an input space that is, 2 by 2. So it helps you building a complex network without exploding your input space. So after you do pooling, now we get into flattening that, and we only flatten because we now want to do fully connected linear combinations in order to actually predict. So when you do want to do a prediction, you sort of need to have a linear combination that you would apply to a certain, what we call a loss function. So that's what we do here. We create a couple of fully connected combinations, and then we do the same softmax output. So the only difference between this and the network we had before is that we added a couple of convolution layers there in order to learn spatial relationship and spatial features. Oh, the thing that I don't have here is the HTML example. I should have had that. But anyway, so this is a way to train your network on a GPU. So we have trained the network on a CPU before. In this case, it's as easy as saying mx.gpu to actually train the rest of the network on a GPU. So in terms of change on the code, just goes that way. So this is supposed to have been training. It's running. And after training, it essentially throws an accuracy score out there. So time check, we have about 10 minutes, so-and-so, right? So I have a third example to a lot of things that happen in the world of deep learning and machine learning is that you see examples with like sample data, which is good, but these are very easy, and these were figured out before, right? So it's hard. When I talk to customers, one of the main challenges that they have is how to train their models on their own data set. And so there is this example that I wanted to show. On how to use MXNet, sorry. Okay. So when you do launch the Deep Learning Army, it looks like that, when the landing page looks like that. So this is another example that is in the examples folder, where you can essentially learn how to create what we call, oh, there's no kernel, sorry. This is the part where, sorry about that. Okay, so essentially in this example, we are going to create our own sample data set, our own training set based on your sample data set, right? So it's very fast to go through. And what you do here is that, oh, sorry. This is actually not what. This is the one I wanted to show. Okay. So what I want to do here is that I want to start with my own data, and I want to create it in such a way, I want to create tensors out of it in such a way that I can use that for training. It's a practical example, and it's also a way for you, if you have your own deep learning problem for image analysis, to just see how other people have done that and then do it yourself. So here, I'm working with a Caltech data set, which is basically a set of images that are of objects that are in about 101 category. Okay. So as I download the data, it's really images into file, like JPEG images into file. And what I want to do is I want to use that to sort of structure that in a way that I can submit it to a deep learning model for learning. That's the goal of this exercise. So with these commands, I download the actual data set, and you can see it happening here, where my code is fetching the data from the Caltech website and then bringing that down to my environment. And so it's putting that in this folder. Download is happening. So it's done downloading. And going back here, what I want to do now is that, maybe I should show you what it actually looks like. So I got the downloads in this folder, right? So what I want to do now is that I want to organize my data set in lists. And then this script does that. So it takes every object in that sort of data set and then builds lists out of it in a way that you can actually use afterwards. And the way you label the structure, the image structure, is that you have the name of the object and then the list and then the number of images that actually represent that image in that folder. And this script goes automatically in every folder and then pulls that out and sort of creates a list of objects and the number of labels that exist out of that. So after you've done that, you sort of need to serialize the data or the list that you have into a format that would actually be used for learning, like creating your tensors, essentially. And that's what you do here. And the last thing is that I use MX.io to create an image record iterator. As you remember, you start with a lot of images, and then you have all these images that you flatten down to create a list. You serialize them in sort of binary type of data set with the labels alongside them. And then you need to create iterators in order to run through the data multiple times so that you can say, give me a batch, give me a batch, give me a batch, reset, give me a batch, give me a batch, give me a batch, reset. And that's sort of what we're doing here. So we create a data iterator, and after creating a data iterator, we use this plot image show for illustration to see some of the images in the data set, right? So right now you can see that it's decoding a few images, and then it's showing us that. So that was the last example. I think this is important because the more I talk to customers, what I realize is that the first thing that I hear about deep learning is that you just plug and play. You just put in your data and it's going to run. It's not true. You have to do some of this. And sometimes they work with sample pre-trained models, which is good, but the challenge is that when you have your own problem, you need to work on your own data and then create your own iterator and train on your own model. And this is the process, right? So it's available online. The last thing I want to show you, we're done, but the last thing I want to show you is where you can find these resources. Sorry about that. We've done this. So I'll give you a minute to copy all of that. No, don't worry. It's here. All right. So if you go to that link, you can have everything you want. All right. So thanks a lot. My email is this. If you want, I'll go back to the link later. So if you want to talk about AI, deep learning, machine learning, MXNet, the cloud, or if you have an interesting workload, shoot me an email. Or if you have a pain point, I'm just an interface. We have a development team, a support team, and everyone that I can tap directly into. So if you have something going on with your workload and then you want to talk about it, reach out to me. I'll reach out to the right people or I'll handle it myself. Thank you.